Okay, so here is butane now. Okay, we have 4 carbons, and I want you to focus first of all on the black atoms that I have here, because those are the carbons. Okay, so here, let me do it this way, and you can see the zigzag, okay, going over here. So that's going to be your butane. Now butane is 4 carbons, so now we can look at these 2 carbons, we can look at these 2 carbons, and then we can also look at these 2. Remember, in Newman projections, or when we're doing conformations, we're only looking at 2 atoms at a time. Okay, so if you look at the first 2, these are going to be similar to the last 2. So what's the point of doing duplicate work, right? So we'll just look at the first 2, and then I'll show you, the different conformations for that. One thing you will note is that when I rotate these molecules, I rotate only 1 carbon, okay, whether it's the front one or the back one, it doesn't matter. Okay, so in this case, because I have a larger molecule, I'm going to go ahead and keep the more carbons at the back. Okay, so remember, we're looking at these 2 carbons. The first carbon has 3 hydrogens. The second carbon here has this ethyl group, which is not really an ethyl group because it's still part of a chain, but just for the sake of simplicity, we're going to say that this is an ethyl group. So you have 2 carbons over here, and then you also have the 2 hydrogens. Okay, so what I'm going to do is I'll go ahead and keep, for the sake of simplicity, the ethyl group, okay, over here at the back. Now you can't see the second one, because the second carbon, because again, it's right at the back, right? So visually it's hard to see, but I'm holding the back carbon, okay, so that I can show you how the movement is going around. All right, and I'll keep moving my hand in case you're having trouble visualizing. But these are the 2 carbons we're looking at, the first and the second. So I'm going to go ahead and start with eclipse. I like starting with eclipse. You don't have to start with the eclipse. Eclipse is when one atom is right behind the other one. Okay, so here is an eclipse, and again, I'll just keep it to the side here so you can see the back atom, right? These are the ethyl groups. So I'm keeping the ethyl group at the top. So now I can rotate it 60 degrees. Another 60, and it will be right behind the other one, or in front of the back carbon. Another 60 degrees, right? Then another 60 degrees, and again, now this one is back, okay? And then another 60 degrees, and now here there is a little bit more room, and then another 60 degrees, and we're back with the hydrogen where the carbon was, right? So, you have 6 structures to draw with 60 degrees rotation, okay, of each. And you can see as we are rotating through, you're probably thinking, what's going on here? I don't see anything very interesting, and that's because there is nothing interesting. Okay, why? Because hydrogen atoms are really small, so they don't really create any kind of problems. Okay, and by problem I mean like steric hindrance or any angle problems. There's nothing going on. So which means what? It means that the first 2 carbons that we're looking at will not matter what conformation they are in. Okay, so now what I'm going to do is we're going to look at these 2 carbons in the middle. Okay, and then we'll see if we have any issues. So again, I'm going to go ahead and keep my big groups on the top. So now if you're looking at these 2 carbons, this carbon has a methyl group, this carbon has a methyl group, and then the 2 hydrogens, and then the 2 hydrogens. Okay, that's what we're looking at. And again, here is our Newman, okay, where you have the 2 carbons right behind each other. So when you look at these 2, I'm going to try and hold it from here so you can see a little bit clearly. So now we have the methyl groups right behind each other. Now you can see the true eclipse in a way, okay? 60 degrees, so I'm going to rotate the front carbon, and now you can see that it is a little bit away from the methyl group. Another 60 degree, now the methyl group is in front of the hydrogen. Now when I bring it down here, okay, at a 180 degree from before, now you can see the methyl groups are far away from each other. Another 60 degrees, another 60 degrees, and then here we are back, okay, to the 60 degrees. So here you can see a little bit more clearly, okay? So what I'm going to do is I'm going to turn the structure around. So this is the eclipse, okay? Look at the eclipse structure. Look at them fighting, okay, with each other. And then when you have the anti, where the groups are far away from each other, look at this conformation. This is the zigzag that we saw before, right? Or generally how we draw. So what's going on here? When you look at these two carbons here with the methyl group on the top and the methyl group at the bottom, now you can see the anti is actually a little bit more favorable because each of the methyl group has its own space, right? So what we say, less steric hindrance. So this is the anti. This is the eclipse where you have these two groups fighting with each other, right? So there is a lot of steric hindrance going on over here. And you can imagine if there were bulky groups even more, like T-butyl groups and all, right? So if you have more carbons, you're going to start having these kind of spatial interactions which are not favorable for the molecule. So the molecule prefers to be like this. So each of these atoms, they have their own space, okay? So this is the anti, which is the lowest energy. This is the eclipse, which is highest energy. This is called staggered or gauche, okay, where they're kind of next to each other. But this one is also not that much favorable as this one is, okay? So 60 degrees, the first 60 degrees, then this one, then the anti, okay, and so on. So that's how it works out for butane. Now you can use this for almost any two atoms, okay? So I was showing you the ethane first. And in the case of ethane, let's say that this blue over here was chlorine, right? So if I use another chlorine over here, so now we have two chlorine. Now chlorine atoms get big. Now let's pretend it's bromine. Bromine is even bigger than chlorine. So if you had bromine atoms, these don't really show the actual space, okay, that bromine is going to occupy, because bromine is a big atom. So if bromine was going to be like this in the case of eclipse, well, then there'll be a lot of spatial interaction here. So this structure, again, now you can see this way, which is the anti. This is going to be a lot more favorable because each of those bromine atoms is going to have its own space, okay? So the best thing to do when you're doing Newman projections is just to make sure that the big groups are anti to each other as much as possible, as far away from each other as possible, to give them more stability. And that is it about conformation. So the bigger the structures, you know, the more interactions you can get, okay?